So now we have constructed the first part of multigrid, which is doing 5 under-relaxed Jacobi iterations. The next is to derive the error equation. Okay, the error equation is this. Let me use a brighter color. The error equation. So we have already defined the solution error to be U exact. I realize I switched the back and forth between X and U, so sorry for the inconsistency in notation, but like they are like the same thing. So I'll make sure I'll use X here. Did I use X or U in this? Oh, I used U here. So let me use the same thing as I used in the code. U exact minus UK. So that is the solution error, right? Let's try to derive an equation that describes the solution error. Because my solution error is smooth on the grid, if I can derive an equation for this error, then I can try to solve for this error on the coarse grid. And after I solve for this error, I can add this error with the solution I have at iteration k. Then I get something close to U exact. Right? Okay, so to derive the error equation, let's put the same matrix onto this. That is equal to U exact minus A times UK. But what is A times? Although we don't know what is U exact, we know what is A times U exact. That is B, right? That is B minus A times UK. And this B minus A times UK, remember last lecture we had a question of how to check for convergence? This is something we usually use to check for convergence. It's called the residual. This is the residual at iteration k. If this residual is small, that means we are closer to convergence. If this is large, that means we are away from convergence. But here, there is another use of the residual. This is something we can compute that defines the right-hand side of the error equation. So A, E equal to R is the error equation we can solve for. Okay? R is the residual we can compute. And we can solve for E on the coarse grid. And then we add the E to the UK to get a better approximation of the solution. That is multigrid. So let me summarize. Operation 1 is smoother. That gives me an error, a EK that is smooth. Okay? And the second step is to solve A E equal to R on the coarse grid. Third step is my U is equal to UK plus this E, right? And there is usually a fourth step that is post-smoothing. That is basically applying the same smoothing operator again to make sure we get a solution that is smooth again. Alright, so that completes multigrid. So we already have step 1 smoother, let's do step 2 now. Yes?
So by smoother you mean the under relaxation?
Under relaxed Jacobi. So under relaxed Jacobi. And it turns out there are also other iterations you can do that can be used as a smoother, but today let's use under relaxed Jacobi. Alright. Basically a feature of the smoother is that it it reduces the oscillatory part of the solution error. As long as you can do that, it qualifies as a good smoother. Yes?
Why are we using a coarse?
Why do I use a coarse grid? What do you think? Yes?
Computational efficiency.
Computational efficiency, right. It turns out that's one thing. Each iteration is cheaper. And there is another aspect of why do I use a coarse grid. Is the convergence itself is actually faster. If I have a coarse grid, the largest eigenvalue is actually further away from 1 than on the final grid. So I get a faster convergence also on the coarse grid. All right. Okay, so let's try to solve the error equation. So let's first compute R. Now, R is equal to the residual. So let's code up another function to compute the residual. Let's also do U and B. And R is equal to this. And because the residual computation is very similar to the Jacobi iteration, I'm just going to copy some stuff in the Jacobi iteration and paste it here, and then start to modify from that. So I also compute n and dx. Instead of u next, I compute the r. And the r of ij is equal to bij minus the summation of the neighbors minus 4 times uij divided by delta x squared. Right? That's a computation of the residual. It's b minus a times u. That's the definition of the residual. It's the right hand side of the error equation we are solving now. Okay, going back to multigrid, R is equal to residual U and B. Now it's the interesting part. We want to solve this on the coarse grid. Alright, so we have to transfer this R somehow to a coarse grid. And the easiest thing to do is just to take the value of R at every 2 grid points. That's called an interpolation operator, or interpolation from fine to coarse. So RC, C means coarse, is equal to R of 1 to end, 1 to end. Are we familiar? Is everybody familiar with this kind of indexing in MATLAB? 1 means it starts, the indexing starts at the first index. This 2 means like for every 2, and this means ends at the very last. Alright? So that's the coarse grid. Okay. And we're going to solve in the coarse grid. And what do we use to solve on the coarse grid? Why not just the multigrid itself? So here I'm going to call the same function I'm coding up here recursively. I'm going to say E is equal to multigrid. And my initial guess would be zeros, because I don't really have a good initial guess. Zeros and divide by 2 plus 1. Oh, I don't have n here. So let me compute n. N is equal to size of u1 minus 1, right? And this is my initial guess, and RC. let me call it EC. All right. Does that always work?
What if n is odd number?
What if n is odd number? So here, n is equal to 1024, right? But as I keep dividing by 2, I'm going to get 1 eventually, right? So I have to put a if n is greater than what? The closest case is when I have 2 grid spacing, so I need the n is greater than 2, right? The whole thing. And okay, so I only solve on the coarse grid if there is a coarse grid. Compute the residual, interpolate the residual to coarse grid, and solve the error equation. And then the next step is u is equal to u plus this EC. In order for me to do this, I need the solution error. I need the error E to be defined on the fine grid. So I need another interpolation for the solution error from the coarse to fine grid. So this is a interpolation fine to coarse. All right, F to C. And here I need the interpolation C to F. So let me say E is equal to the solution error at the fine grid, 0's n plus 1, right? I'll do it here. And my E at, again, 1 to 2 to end, 1 to 2 to end is equal to EC. Is that sufficient? I need to also fill the entries in between, right? Otherwise, I have zeros at the places where I don't have the EC. So I need to interpolate. I really need to interpolate. So here I will just use the plane average. So E of 2 to 2 to n minus 1. So that is the starting from the second index. That's the part I don't have value. Is equal to 0.5 times the sum of this plus okay, so instead of 2 to n minus 1, I have 3 to n and 1 to n minus 2, right? Basically, I'm taking I'm taking the 2 adjacent rows and average it to the rows that I don't have value yet. And I need to do the same thing to the columns. To the columns. All right. So that completes my interpolation from coarse to fine. Any questions on that? Next step, U is equal to U plus E. Right? That's basically adding the solution error to my previous iteration to get a better approximation of U exact. That comes from the definition of this error. If I solved the error equation exactly, then my E plus U would be the exact solution. Of course, I'm using multigrid. I'm still using iterative method, so I don't have the solution E exactly, but hopefully I get a good approximation of E, so I get a better approximation of U exact.